Hello friends, in this video I'm going to answer this question which is based on central force problem. Okay, a particle of mass capital M moves on a plane in the field of force given by this force. This is the central force. Okay, and here K is constant, R cap is the unit vector along the radius. And will the angular momentum of this particle about the origin be conserved? We have to answer this, and we need to answer to this question as well. Use Lagrange equation to find the differential equation of orbit of the particle. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT 123. That's my Insta ID. Okay, so now let's start. Now it is given that the particle of mass capital M is moving on a plane under this central force. This is the central force, right? We know that central force can be represented by this form. F is equal to small f of r. Let me write it this form, r cap. Okay, we know this can be written in this form, where this f of r, this is nothing but minus del v del r. Okay, so v is the potential here. So here we can write, we know that central force can be represented by this, right? Now if we compare these two, what we can have here, you see this is nothing but minus here rKcos theta r cap. We can write this way, right? So if you compare these two, then what you can have, you can have f of r is equal to minus k r cos theta. That's what we're gonna have, right? Now you see here, take this relation. So here, let me copy this. So here you see, now if we simplify this equation, what we're gonna have, we're gonna have del v is equal to minus f of r del r. That's what we're gonna have, and we can replace this f of r by this expression, right? And if we do so, then what we're gonna have, that's gonna be equal to, there is already one minus and there is also minus, so it's gonna be plus k r cos theta. That's what we're gonna have. Then here we have del r, sorry. So now let us integrate this. If we integrate both sides, then what we're gonna have, integrating both sides, v will be equal to, so differential coefficient will be removed on integration, and here k r cos theta dr. So here, just give me a second. So here k cos theta, that will be taken out of the integral, because we are differentiating with respect to integrating with respect to r. Here we have del r, right? So cos theta integration r del r, that's what we're gonna have. If you integrate this, then it's gonna be r square by 2. Here we're gonna have an integrating constant. So this is the potential, right? So hope you have understood this. Now you see, we know that Lagrangian L is given by kinetic energy T minus potential energy V, right? So let's find the kinetic energy first. So let me write here, kinetic energy T is equal to, that particle under central central force, the kinetic energy of a particle under central force, there will be two types of kinetic energies. One is due to angular motion, another is towards the radius, that will be given by half. Here mass is m, so m, we know kinetic energy half mv square. V is nothing but v velocity, that means I'm not talking about this v which is potential. So here velocity will be given by derivative of r, right? So that's why r dot, I'm writing r dot means dr dt, which gives the velocity along the radius, okay, square, velocity square, half into mass into velocity square, and one is due to the angular motion. So here that angular velocity is r theta dot. Here we're gonna have velocity square, so square of this, that's why we're gonna have r square theta dot square. So mass into r dot square, then mass into this angular velocity square. So taking the mass common here, we have got this kinetic energy of the particle under central force, right? So here we have got kinetic energy, and here we have got potential energy as well. So therefore the Lagrangian L is equal to, let me use the black, T minus V. So here let's put the kinetic energy here. This is T minus V. V is this, right? So here we're gonna get this. This is V. So that's gonna be minus C now, right? Because of this minus, right? So this is what we have got Lagrangian. Let me copy this and let me go to a new slide. Okay, so here is the Lagrangian that we have got. So let me write this one here. So now you see Lagrange equation for theta, Lagrange equation, so we know that gonna be ddt of del L by del theta dot minus del L del theta is equal to 0. That's gonna be the equation, right? So now you see here, let me write it properly. This is theta dot, okay. So now if you differentiate this with respect to theta dot, here this part is the only function of theta dot. So that means if you multiply this one with this, then what you're gonna have, half capital M r square theta dot square. If you differentiate it with respect to with respect to theta dot, okay, then what we're gonna have, half M r square into 2 theta dot. That's what we're gonna have. Then 2 will be cancelled, so M r square theta dot. That's what we will get. So here we're gonna have ddt of M r square theta dot minus, not minus, plus, again you see, if you differentiate this part with respect to theta dot, that's gonna be 0 obviously. Now minus del L by del theta. So now here you see, here is the only function which is a function of theta. So that's why derivative of this part with respect to theta will be 0. So we're gonna get only this part. If you differentiate this, minus k cos theta r square by 2, if you differentiate this with respect to theta, then then minus k, derivative of cos is sine, minus sine, then r square by 2, here minus minus, that's gonna be plus. So we're gonna left with k r square by 2 sine theta is equal to 0. That's what we have got, right? So hope you have understood this. So let it be equation number 1. Okay, now you see this part is nothing but angular momentum. So in case of motion under central force, the angular momentum is constant, because you see actually I forgot to explain this first question. Okay, first let me explain that. I will continue this one also. So for answer to the first part, you should write like this. Now you see, since the central force F is nothing but F of r cap, right? So now we know that angular momentum, derivative of the angular momentum, if L, let me suppose so I'm not going to use L, let me use J, because here I'm using L for Lagrangian, so that means that's why let me use J for angular momentum. Relation between the angular momentum is this, right? This is the relation between the angular momentum and torque. Relation between angular momentum J and torque tau is given by this relation, right? Let me write it properly. Is given by this relation, and torque is equal to r cross F, right? R cross F, right? And now you see this force, the central force, here we have r cap, that means this force is directed along r. So that's gonna be here, you see, r F sine 0 degree, since r and F both or you can say since F is acting along this r vector, so that's why this torque will be equal to 0. If this is equal to 0, derivative of this is equal to 0, that means this J, that means angular momentum must be constant. So that must be constant. So this is the answer to this first part of the question, this one. Here is, will the angular momentum of the particle about the origin be conserved? So here we're gonna conclude that yes, or you can write, therefore the angular momentum of the particle about the origin is conserved, right? So that is the first part of the question, answer to the first part of the question. Now let me continue here. So here actually second part of the question is started here. So now let me continue. Here you see, this is the expression for actually angular momentum, m r square theta dot, this gives nothing but angular momentum, which is equal to J, and it is constant. It is constant here, right? So if this part is constant, then this derivative of this with respect to time, that's going to be equal to 0. So we're going to have k r square by 2 sine theta is equal to 0 here, right? So hope you have understood this. Now for r, let me obtain the Lagrange equation for r. So let me copy this Lagrangian and let me go to a new slide. Okay, so this is the Lagrangian. Now for r, radius r, Lagrange equation it can be written in this way, that the dt of del r, sorry, del l, del r dot minus here del l, del r is equal to 0. So that's how we're gonna write the equation. Now here you see, let us differentiate this. So here this is the only function of r dot, this part. Okay, so this part is function of theta dot, not r dot. Here we have r but not r dot. So if we differentiate this half m r dot square with respect to r dot, then what we're gonna have, half m 2r dot, that's what we're gonna get. So here m r dot, okay, and derivative of this part becomes 0, and derivative of this part also becomes 0, and this is obviously constant, that's gonna be, you know its derivative will be 0, right? So we end up getting time derivative of m r dot minus, then if we differentiate with respect to r, then here you see this part is the function of r. So from this part what we're gonna have, half m r square theta dot square. If you differentiate with respect to r, then here half m 2r theta dot square. So here r are gone, so we can have m, let me write it properly, m r theta dot square. Then here also you see this is also function of r. So if you differentiate this, here 2r and this 2 will be cancelled, so we're gonna have minus because of this minus sign, sorry, because of this minus sign and this minus sign, so we're gonna end up getting positive here. So k cos theta r square, instead of r square we're gonna get r, because here we should get 2r divided by 2 to cancel, right, on differentiating with respect to r. That's what we have got, that is equal to 0, and derivative of constant obviously 0, right? So hope you have understood this. So now you see what we can do here. We have to obtain the r dot and r double dot. Here you see, okay, we can write this part this way, that r double dot, because you know r dot is dr by dt, and if you differentiate it again, that's gonna be second order derivative, which can be represented by r double dot, right? Hope you have understood this. So that's how we have got this part. Now you see m r theta dot square plus k r cos theta is equal to 0. Let it be equation number 2. This is equation number suppose 2. Okay, so now you see, let me go to the previous slide, and from this part here, now here you see, from this equation what we will obtain, we're gonna get theta dot is equal to z by m r square, right? We're gonna use this relation. Okay, so now you see, first let me obtain this r dot. Okay, let me copy this equation number 2 and let me take a new slide. So first express this in terms of r theta dot. Okay, now you see r dot can be written as ddt of r, and it can be written as, you know, this in terms of theta. We can write this way, we can use the sine rule actually. Okay, we can use this chain rule, and this is nothing but theta dot, time derivative of theta, which is nothing but theta dot. So now you see, now this theta dot can be replaced by this, right? So let me copy this. Okay, we're gonna use this relation. Instead of theta dot, we're gonna put dr d theta. Instead of theta dot, we're gonna write j m r square, j by m r square. That's what we have got. So now r double dot, okay, so it can be written this way, time derivative of r, right? And that can be changed by this, right? Hope you have understood this. Right, now you see here, this r dot will be replaced by this result. Then what we're gonna have, let me write here. So here, let me copy this. This is nothing but r dot, okay? Then again here, this is theta dot, okay, this is theta dot, okay. Now you see, again this theta dot will be replaced by this result, okay. Now this theta dot will be replaced by this result. So what we're gonna have, so now you see, from here, now let me put this one here. Then here you see, this m, j by m can be taken outside the differential, right? So we can write j by m d d theta 1 by r square dr by d theta, and again theta dot is replaced by j by mr square. So we end up getting, after multiplication, we're gonna have j square by m square r square, then again derivative with respect to theta of 1 by r square dr by d theta. That's what we're gonna have. Okay, now we are to replace this r double dot by this result and theta dot by this result, okay. So using this result in this equation number 2, okay. So therefore from equation number 2 implies that capital M, so r double dot will be replaced by this result, okay. So let me copy this result, just let me put directly, okay. Just give me a second, let me readjust these things, okay. So now let me copy this one here, let me put this one here instead of r double dot, okay. Okay, just give me a second, okay. So here we have put this one instead of r double dot, okay, m into, so instead of r double dot we have replaced this, okay. So then here theta dot square, that will be replaced by, so now you see, minus m r theta dot square is nothing but, let me write this one here, j m r square, right? So this is theta dot square, so here we need to put square here, then plus k r cos theta is equal to 0, That's what we're gonna have, right? So now let me copy this result and let me go to a new slide. Okay, so now, so here you see this m cancels m square, so we're gonna get m only. Then okay, here you see, so this part gonna be equal to mr into j square by m square r to the power 4. So if you cancel r by r square 4 by r to the power 4 by r, then you're gonna get r cube, then m cancels m square, right? So here this term gonna be equal to j square by m r cube, right? That's what we're gonna have. Hope you have understood this. So now the final equation will be of this form, j square by m r square. Okay, so let me put this one here, then minus 1 by j square, minus j square by m r cube plus k r cos theta. So this is the required equation of the orbit. Okay, so this is the required equation of the orbit, and this equation also can be simplified as this, considering u is equal to 1 by r, suppose. Okay, let u is equal to 1 by r. In that case, you see del u del theta, if you differentiate u with respect to theta, then what you're gonna get, that's gonna be derivative with respect to theta of r to the power minus 1, because u is equal to 1 by r, right? So if you differentiate it, so here you say this is not partial derivative, so you cannot consider this r as constant while you are differentiating with respect to theta. But in case of partial derivative, it can be it will be 0 if you differentiating with respect to theta, but you are differentiating a function of other variable, then it will be 0. But now it is not partial derivative, so here we're gonna get minus 1 by r square. So again we have to write del dr by d theta. So that's why what we can do, if you make it positive, this is going to be negative, right? So we can write that minus du by d theta is equal to 1 by r square dr d theta. So that's why we can replace this part by this. Okay, then this equation gonna be equal to, now you see, j square by m. So now as u is equal to 1 by r, so 1 by r square, that's going to be u square. So here we can write u square, again d theta of minus du by d theta. So minus j square by m, here we're gonna have u cube plus k by u cos theta is equal to 0. We can write this way. Okay, and this part is nothing but second order derivative of u with respect to theta. We can write this way, right? So this is the differential equation. Okay, this is the required differential equation. So this is the required differential equation. Okay, so hope you have understood this. Thank you for watching. See you in the next video. Bye bye.